This is the second part of section 7.4. And here we're going to be talking about surface area. Of rotations. Okay, so the first thing then, well, let's sort of set up what these things are going to look like in a problem. So you're going to have some function here. And we're going to take it over some interval, a to b, and we're going to rotate it, let's just say, around the x-axis. You can also rotate this around the y-axis. Now, what we did before was we were looking for volume, where we took this whole thing, we rotated around, and we're looking for volume. What we're looking for now, though, is just this surface area as we rotate it around. So the nearest thing I can think of that's an analog to this is to get yourself a styrofoam cup. And this might not be a bad thing for you to do. Pause it and go and get yourself a styrofoam cup and then take a look at it. Styrofoam cup is an example of a frustum, which is a cone with the tip chopped off. Okay, and basically what these are going to look like, if you turn it on its side, is we will have something like this, all right? The area we're going to be rotating around, or the axis we're going to be rotating around, comes right through the middle here. All right, it goes through the middle of this thing. And if you take a look, we've got a radius here. We'll call that R1. And we've got a radius here. We're going to call this R2. And then we've got a length, which is going to be L. And the formula for area of a frustum is basically, so the area of a frustum is 2 pi R1 plus R2 times L, which is this slant distance here. Okay? Now, what we're going to do here on these things in calculus is we're going to come in and make L, or let's write this in formal notation. We're going to take the limit as L goes to 0. In other words, I'm going to make L very, very, very small. So the limit as L goes to 0, R1 is going to equal to R2. And so we're just going to call that R. So the limit of a frustum with very, very small length, and what we're talking about here is just sort of taking the slice out of this thing, is then the area is going to be 2 pi R, and then this very small piece along here, ds. In other words, what I'm saying is that the limit as L goes to infinity of L is going to be ds, which is a very, very small arc length. And that's what we're dealing with here. So what we're going to do then is we're going to take these very, very thin frustums, and if you want to think about this as being a styrofoam cup with basically almost no height at all. It's very, very, very small. We're going to shrink our cup until it has almost no height at all. Okay, and when we do this, then the area total is going to be 2 pi times the integral between a and b of r ds. Okay, and if you remember, we'd already talked about this small length in here. We did this last time. So ds is basically our small arc length. That we were integrating before. So ds is going to be the square root of 1 plus dy dx squared. And this ought to look familiar. Okay, so if we plug all of this back in, so my area then is going to equal to 2 pi times the integral from a to b of r times the square root of 1 plus dy dx squared dx. All right? So now let's come in and take a look at what this r is, and let's go back to our original picture, which is right here. R is basically just the distance from our axis of rotation to our curve. All right? So R is the distance from axis of rotation to the curve we are rotating. Well, this doesn't sound too bad, and it's not. Again, like arc length, the calculus itself is relatively straightforward. It's the algebra that can get to be kind of a pain. Okay, and again, okay. And this works no matter what we're rotating it about, okay? We come back and illustrate that. Your book was talking about, they had two different things for this. They also had dy. But basically, if we hold on with this, as long as we define r here to be the distance from our axis of rotation to the curve, then the route which we're rotating, then this is going to be the same. And this will work. Let me illustrate what we're doing then before I go on. So for instance, if I took the same curve I had before, which was this guy, but now I'm going to rotate it about the y-axis, all right? Now again, this thing is going to be some function of x. And we're still all right. But remember before, my r was here. On this one, my r is going to be this distance, which if you take a look at it, is my x value. Okay, so this is the r that we're interested in. And my ds, my arc length, is still just this little length across here. So really, we don't change anything depending upon whether rotating it, whatever we rotate it about, except for this r function, which is just the distance from whatever we're rotating about to my curve. Okay, so let's work a couple of examples, one about each axis. So the first example I'm going to do is we've got my function is 1/3 x cubed. We're going to revolve about the x-axis And we're going to do this between, or on the closed interval, 0 to 3. Okay. So the first thing I'm going to do is basically graph this thing. And 1/3 f of x looks like this. And I'm rotating it about here. So this is y equals 1/3 x cubed. And we're going to go between 0 and 3. So here is my curve. And if we rotate this around the x-axis, you can see it's going to end up giving us something with a flat bottom here. And it's sort of a vase shape kind of thing, okay? If you rotate it around like that. Okay, so that's sort of what our surface is going to look like. So let's come back in then and take a look at it. Rotating about x, so my r is going to be distance from x up to my curve, which is going to be my y value, which is given by this. Okay, so now we're ready to start putting stuff in and finding this. So my area is 2 pi times the integral from 0 to 3 of my r is going to be 1/3 x cubed. So divide by 3, I'm going to have x cubed. And then my ds, my arc length, is going to be the square root of 1 plus dy dx squared. Okay, so now we're ready to go. Except we need dy dx. Oops. So that's going to be the derivative of 1/3 x cubed. So I multiply by 3 and subtract 1, so that's going to be x squared. Okay, so there's my derivative of the thing. And now I'm ready to plug in and try to integrate. This is where things can get a little bit sticky. So my area then is going to be 2 pi over 3 times the integral from 0 to 3 the square root of 1 plus x squared dx. And I've got an x cubed out in front of here, which is my r. Okay, so my area then is 2 pi over 3 times the integral from 0 to 3 of, I'm going to rewrite this, of 1 plus x to the 4th to the 1/2 x cubed dx. So I'm going to look and see if I've got a u substitution here. So my u is 1 plus x to the 4th. Then my du is going to be 4x cubed. Sure enough, I've got that. So I'm in good shape then. So now we come back in, except I'm going to have to divide by my 4. So my area then is going to be 2 pi over 4 times 3 times the integral from 0 to 3 of u to the 1/2 du which is 2 pi over 12, so area is going to be pi over 6. And then I'm going to integrate this guy, so I add 1. which gives me 3/2. So I'm going to have u to the 3/2, and I multiply by the reciprocal, 2/3. Or area is going to equal to, this gives me 2 pi over 18, which is going to be pi over 9, times 1 plus x to the 4th to the 3/2. And this will be evaluated between 0 and 3. So now we come back in and plug our numbers. So my area is going to be equal to pi over 9. This should look familiar from the homework you were doing the other day. Times 1 plus 3 to the 4th to the 3/2 minus 1 plus 0 to the 4th to the 3/2. And if we plug all of this in, this gives me square root of 82 over 2. And it'd be approximately equal to 258.58. And there's that one. Okay, let's do another example. One more example here. And this one, I'm going to rotate about the y-axis. So my function then, what? So here's my second example. My y is going to equal to the cube root of x plus 2. We're going to rotate about y-axis. And we're going to work on the interval 1 to 8. Yeah. Okay, so the first thing I did was go in and graph this guy. It starts at 2, and it looks like this. And we're going to rotate this thing about this. So if you look at it then, and between 1 and 8 actually, I'm going to have a flat surface, and then we'll have something which looks like this. Sort of similar to the other one, but the other one was lying on its side like a speaker. This one is facing up. Okay. So let me clear this back up. Here is my function. And we're going to go from 1 to 8. So my r then, and we're rotating about here, is going to be the distance from here to here, which is whatever my x value is. So r is going to equal to x. Well, that's nice. Now you say, well, but we've got a washer, and the answer is not really. This just gives us a flat surface. But since we're only integrating between 1 and 8, all right, we're not going to add any surface area in here, so we take care of this gap by what we are integrating across. Now because this it's not going to add, the bottom is not going to add any surface volume to us. We're assuming it's open. So yeah, if you poured water in here, it would be running out here. Okay. So I guess less like a vase and more like a funnel, although funnel with curved sides rather than straight ones. Okay, so there's that one. So now we're ready to go in. We've got our R, and we want to come back in. So my area then, if you remember, is 2 pi times the integral from a to b of r ds. I've got my r, So area is going to be equal to 2 pi times the integral from 1 to 8 of x, and ds is the square root of 1 plus dy dx squared. So to do this, first thing I need to do is find my dy dx going to equal to the derivative of x to the 1/3 plus 2. So to do the derivative, you multiply by that, by our power, our exponential. Give me 1/3, and then I subtract 1, x to the negative 2/3. And the derivative of 2 is 0, which is going to be 1 over 3 x to the 2/3. Okay, so now we're ready to plug this puppy in. So area is going to equal to 2 pi times the integral from 1 to 8 of x times the square root of 1 plus 1 over 3x to the 2/3 squared dx. This will be 2/3. All right. And then the area is 2 pi times the integral from 1 to 8 of, so now I'm going to have 1 plus 1 over 9x to the 4/3 to the 1/2 times x dx. So what I want to see then is if I've got a u sub, and I can tell you right now we don't because of this thing. But even if we did, let's come in and take a real quick look. So I'm going to have 1 plus, and this is going to be 1/9 x to the negative 4/3. And if we do that, that's going to give me a negative 4/27 x to the negative 7/3, which we do not have. We've got an x, and that's it. We do not have x to the 7/3. So u sub is out. So how are we going to do this? Don't scream at your calculus teacher. What you need to do then is get a common denominator in here. So my common denominator is going to be 9x to the 4/3. So I'm going to have, and I'm just going to deal just with this part of it now. So I'm going to end up with my denominator then will be the square root of 9x to the 4/3. And then on the top, I'm going to have the square root of 9x to the 4/3 plus 1. All right. For right now, I'm going to leave the top alone. So I've got 9x to the 4/3 plus 1 to the 1/2 over 9x to the 4/3 to the 1/2. Remember, we multiply these things. So now I'm going to end up with a 9x to the 4/3 plus 1 over 3x to the 2/3. All right, and this is to the 1/2. So what I've done here now then, if you take a look, if you see, is I've pulled all my stuff out. So now I'm going to come back in, and I'm going to have x. This will be I'm plugging back into my integral. I'm going to have 2 pi times the integral. And I'm dividing by 3, so I'm going to pull that out. And I'm going to have 9x to 4/3 plus 1. This is going to be times x from my original times x to the negative 2/3, which is what we pulled from here. And I'm going to simplify this out, and what's going to happen now is we're going to end up with a u sub. So now I've got 2/3 pi times the integral from 1 to 8 of 9x to the 4/3 plus 1 times x to the 1/3 dx. So now this is going to be my new u. So u is going to be 9x to the 4/3 du, then will be 9 times 4 is 36, so that will give me 12 divided by 3, x to the 1/3. Subtract 3/3 from this. Notice we've got this here. So now we can do a u sub, thank God. Except we got to divide by 12. So I've got 2 pi over 12 times 3 times the integral from 1 to 8 of u to the 1/2 du. This we can do. This simplifies to 1 over 6. So I'm going to end up with pi over 18. And then I'm going to integrate u to the 1/2. All right. So I'm going to add 1. That's going to give me u to the 3/2. Now multiply by the reciprocal, which is 2/3. Then we're going to evaluate our x equals 1 to 8. Not u, but x. Or if I do that, I end up with pi over 27 times 1, oh, there it is, 9 x to the 4/3 plus 1 to the 3/2. Evaluate from 1 to 8. And then, so my area then becomes pi over 27 times 9 times 8 to the 4/3 plus 1 to the 3/2 minus 9 times 0 plus 1 to the 3/2. And when you do all of this out, area works out to be approximately equal to 199.48. So if you take a look, this incorporates basically a lot of things we've been dealing with. The rotations we were talking about for volumes of rotation, where we moved them around an axis. We're doing the same thing again. But then this time, instead of dealing with the volume, we're dealing with the surface area. So this, we bring arc length back into this thing to take care of it. And our radius, if you remember, our little r, is defined to be the distance from our axis of rotation out to whatever the curve that we are rotating is. And then you just come back in. Now remember, this was done about the y-axis, but I integrated about x because the integration here is involved with the arc length, and my radius that we found in the beginning was just x. So unlike with volumes of rotation, where we had to actually go in and solve for x equals y, on this you don't have to do it if you're clever enough in finding your r. So this is how you're going to do these things.